guys, so in this video we are covering key features of rational functions. Specifically, we're going to be looking at asymptotes and x-intercepts and y-intercepts. Okay, so before we do that, I do want to do a couple of review questions. Now these review questions are on the real world problems with rational equations to solve them. So looking at the first one, it says a plane flew 720 miles with a steady 30-mile-per-hour tailwind. The pilot then returned to the starting point, flying against the same wind. If the round-trip flight took 10 hours, what was the plane's airspeed? Okay, so that's what we're looking for. Let's call the airspeed x. And we knew that their total round-trip flight, this is how much time it was, okay? So the time to go there and the time to go back, okay? So we'll call this going there and then back, okay? So the time, we'll call the time there t1, and the time back, we'll call that t2. So time 1 plus time 2 is a total of 10. Now it could be 5-5, it could be 6-4, we don't know. We don't know what the times specifically are, but we know that round trip, there and back, 10 hours total. The other thing that we know is that they flew for 720 miles. That distance, okay, distance for, this is time, the distance for both is the same, right? It doesn't matter whether you're going there or back. The distance to go there is 720 and the distance to come back is also 720. The next thing that we have to talk about is the rate, right? How fast were we flying? Now they do say that we have a tailwind, right? So the pilot returns to the starting point. On their way back, they're flying against the wind. So flying there, they're flying with the wind. So whatever their airspeed is, plus the tailwind 30, will be how much they actually had a speed. And then on their way back, they're flying against the wind, so that would be whatever their airspeed is minus 30. Okay? So the time, remember that time, right, is distance divided by rate, because distance equals rate times time. So if you're solving for time, then you would divide by r, divide by rate. So time equals distance divided by rate. So the time for there would be the distance for there, 720, divided by the rate for there, which is x plus 30. And then the time for back, t2, time back, would be the distance going back, 720, divided by the rate going back, which would be x minus 30. And altogether, adding those two will give you 10. Okay? So I'm going to go ahead and make all of the denominators the same. That way we can cancel out the denominators since we have an equation here. So I'm going to multiply the top and the bottom of this fraction by x minus 30. And I'm going to multiply the bottom and top of this fraction by x plus 30. And I'll have to multiply the top and the bottom of this fraction by both x minus 30 times x plus 30. Okay, now that the denominators are all the same, they cancel. We get 720x minus 720 times 30, which is, let's see, 720, oops, 720 times 30 is 21,600. And, oh, plus 720 times x would be 720x, and 720 times positive 30 would be positive 21,600. Okay. On the right-hand side, we have 10 times x minus 30 times x plus 30. You can either multiply 10 in here first, then multiply both terms by x plus 30. I'm going to do it multiplying these two first and then distributing the 10. So I'm going to multiply these two would be x squared. And then the middle term would cancel. Negative 30x plus 30x would cancel. And negative 30 times positive 30 is negative 900. So then I'm going to distribute 10, and I'm also going to combine like terms here. Negative 21,600 plus 21,600 would cancel, and 720 plus 720 is 1440. And over here, distributing 10, we would get 10x squared minus 9,000. Okay, so now you see that we have a highest power of 2, which means we have a quadratic. So I'm going to go ahead and bring over the 1440x to the right-hand side by subtracting it. So now I have an equation, 0 equals 10x squared minus 1440x minus 9,000, excuse me, and I need to solve for this. Now I can actually factor out 10 from all of these, so I'm going to factor out 10, and we get x squared minus 144x minus 900. And then now I need two numbers that multiply to negative 900 and add to negative 144. So let's go through. Negative 900 divided by 4. Nope, that doesn't work. Negative 900, let me try something a little bit higher, divided by 9. No, something less than that. Negative 900, because 100 is too big, divided by, let's try 5. Nope, something a little bit higher. Let's try 6. Yes, so negative 150 plus 6 would give me negative 144. So this will factor into x, was it positive 6 and x minus 150. So that means I have x equals negative 6 and x equals 150. Now, there's a real world problem. What does x represent? X represents our airspeed. So can we have a negative 6 airspeed? No. So our airspeed is 150 miles per hour. Okay, let's go ahead and do number 2. Now number 2 is actually a little bit easier. Pauline can bicycle 75 miles in the same time, so the time is the same, that it takes her to drive 165 miles. If her driving rate is 30 miles per hour faster than her rate on the bicycle, find each rate. So we have two things. We have bicycling and we have driving. Okay, so we need to go ahead and write our distance. Oops. Our rate and our time, right? Now, what is the bicycle? The bicycle distance, right, is 75 miles. And the driving distance is 165 miles. Obviously, it would be quicker to drive than it is to bike. And then the time is equal, right? So the time for bicycling is equal to the time driving, because they're bicycling and driving the same amount of time, but the distance that they go is different because the rate is different. So now let's talk about the rate, right? Her driving rate is 30 miles per hour faster than her rate on the bicycle. So whatever her rate on the bicycle is, let's go ahead and call that X. Her driving rate is 30 more than that. So her driving rate would be X plus 30. I'm trying to make a table here, but it's not coming out very well. There we go, that's a little better, I think. All right, so if we make X is her bicycle rate, then her driving rate would be X plus 30. So let's go ahead and write an equation, right? We know that T1 equals T2. Now time, what is time, right? We have that time is distance divided by rate. So the distance of the bicycle, 75, over the rate of the bicycle, x, equals the distance of driving, 165, over the rate of driving, x plus 30. And this is a proportion, one fraction equal to one fraction, so we can cross multiply, right? X times 165 equals 75 times x plus 30. And remember, we have multiple terms, so 75 times x would be 75x. 75 times 30, I think, is 150. Let's verify that. 75 times 30 equals, way off, 2250, so 2250. So x times 165, which of course would be 165x, and now we just solve. Let's subtract 75x on both sides. So we get 2250 equals, I believe 165 minus 75 is 90, but you know, let's just verify. You never know. 165 minus 75, sometimes you think and you're thinking incorrectly. There we go. That was good. And then solve by dividing 90 on both sides. So we get x equals, and I'm going to verify this answer with a calculator. So 2250 divided by 90 is 25. Now, what's the question? The question is, find each rate. I just found x. What does x represent? X represents the bicycle rate. So this is the rate for bicycling. So she's going 25, and this is miles per hour, while bicycling. And going how many miles per hour while driving. So what is her rate driving? Well, her rate driving is whatever her rate bicycling is plus 30. So 25 plus 30 is 55. All right. Okay, so that's it for the review questions. Let's go in and talk about the key features, okay? Now, we're going to, in the next topic, talk about graphing rational functions. And in order to graph them, we are going to need to find these key features. So remember that a rational function is just a ratio of two polynomials, right? So the parent function to the rational function is right here. It's f of x equals 1 over x. That's the most simple rational function that we could come up with, right? Just f of x equals 1 over x. 1 is a polynomial, x is a polynomial. So that is the most simple that we can get. Now, the rational function for f of x equals 1 over x is actually graphed right here. So if you notice, and the graph is the blue, okay? The graph is the blue. If you notice, you have this vertical dashed line here, and you have this horizontal dashed line here. And that's because rational functions very often have what are called asymptotes, okay? Asymptotes are straight lines which the curve of the function approaches, okay? And you cannot ever cross a vertical asymptote. So for a vertical asymptote, the graph will get very, very, very close, infinitely close to that vertical line, but it will never actually cross it. Now you can actually cross horizontal asymptotes or slant asymptotes, which are also called obliques. But you can't cross vertical asymptotes. Now, more often than not, you don't cross the horizontal asymptotes either, but you can. It is possible that you cross them, okay? Now, if you look at this example here specifically, right, you see that the horizontal asymptote is at y equals 0, and that a vertical asymptote is at x equals 0. Those are the line equations, right? You know that a vertical line is always x equals whatever x value that vertical line goes through. And then a horizontal line equation is y equals whatever y value that horizontal line goes over. So those, you always write the asymptotes as the equation of the line, right? Now, obliques we'll talk about a little bit later, and obliques are slant ones that are linear. They're still lines, but they aren't exactly vertical or exactly horizontal. They can be like diagonal, okay? So if you notice, we do approach very close, and if I extended the graph here, this would continue and get very, very close, and it's going to start looking horizontal. Just because it starts looking horizontal does not mean it is horizontal. The graph is always at a slant, getting closer and closer to that asymptote. If you were to infinitely zoom in, you would see that it's getting closer and closer, but it never actually touches it or crosses it, right? So same thing on this side. It is getting closer and closer to this vertical asymptote, but it's never actually crossing it. So that's what an asymptote is, right? Let's first talk about vertical asymptote and holes, okay? These are discontinuities in the domain of the rational function. So what does that mean? That means that that value is not defined in the function, right? So if I look up x equals 2 here, there is no value, right? It's undefined. Whereas if I look at x equals 0, well, I have a point here. The y value for x equals 0 is 0.5, negative 0.5. So any vertical asymptote will be that break in the domain where you don't have any value, and there is no point for the function at that x value. So a hole is also the same thing where there is a break, but the difference between a vertical asymptote and a hole is you could see that a vertical asymptote changes the behavior of the graph. So if you notice, the graph will get infinitely close to that vertical asymptote on both sides, versus this is an example of a hole right here. It's just like a quick break and that's it. So a hole will not change the behavior of the graph or affect the behavior of a graph. It will just be a missing point. And a vertical asymptote will be completely changing the behavior of the graph. So how you find a vertical asymptote and a hole is the same way. You find the zeros that are in the denominator. So you find whatever makes the denominator 0. These would have been what were before our excluded values. So the difference between the two is a hole will come from any 0 that cancels out. So for example, here, x minus 2 would cancel out. So that factor, x minus 2, gives us a 0 of, an x value of 2 will give us a 0 in the denominator. So that means that the hole is at 2, because that cancels. If you notice here, we also have the denominator can't be 2, because then the denominator will be 0. But here, that x minus 2 factor doesn't cancel. So that's where you get the vertical asymptote. So in other words, what you do is you find what are the excluded values. If that excluded value came from a factor that you were able to cancel, it's a hole. But if you aren't able to cancel that factor, then it's going to be a vertical asymptote. Now, the important thing to know here is that you could have more than one, okay? You can have more than one vertical asymptote. It's whatever values, or holes, whatever values make the denominator 0. If that factor cancels out, it's a hole. If it doesn't cancel out, it's a vertical asymptote. So let's try some. So I'm identifying points of discontinuity. These are the points where the graph is discontinuous, so these are the vertical asymptote and the holes that we just talked about. Now, those come from getting the whatever makes the denominator 0. So let's go ahead and factor the denominator first. So the denominator, the coefficient is 1, so it's very easy factoring. Factors into x minus 1 times x plus 3. Okay? Now, on the numerator we have x plus 1, and on the denominator we have x minus 1. So that doesn't cancel. So we have two vertical asymptotes, VA, one at x equals 1 and another one at x equals negative 3. There are two of them. You always want to write the asymptote as a equation because it represents a line, right? And that's it. Now, go ahead and pause the video and try number 2 on your own. All right, so first let's go ahead and factor the numerator and denominator. So we have f of x equals, and we actually already factored this before, it factors into x minus 1 times x plus 3. The denominator would factor into x plus 4 times x plus 3. And now you can see that we can cancel out x plus 3 on top and bottom. So that 0, which would be negative 3, is actually where I get my whole from. So that is the x value of the whole. Something that's very important for me to note that I should mention is that the whole is a point, right? Because that's what it is. It's just a missing space right there. So it's just a point that is missing on the graph, that is empty, right? That you graph it with an open circle. So that is actually a point versus a vertical asymptote is a line, right? So that's why you write the vertical asymptote as a line equation, but when you write and describe a whole, you write it as the x and y coordinate point that is missing an empty open circle. So let's go ahead and find the y value. Now, a very important thing is when you're finding the y value of the whole, you have to use the simplified version of your function. If not, you're going to end up with 0, okay? Because it's a factor that cancels on the numerator and denominator, so obviously it makes both the numerator and the denominator 0. So you always have to use the simplified version of your function. So x minus 1, negative 3 minus 1, over x plus 4, negative 3 plus 4. So we end up with negative 4 over 1, so our output for that input of negative 3 is negative 4. And again, this is actually an empty whole. If I were to graph it, I would graph it as an open circle at that point, okay? Now, for a vertical asymptote, what denominator stayed? The x plus 4 stays, right? So that is where we get our vertical asymptote from. The 0 here would be negative 4. So this vertical asymptote equation, x equals negative 4. And that is our vertical asymptote. All right, awesome. So a horizontal asymptote is a horizontal line, right? And again, same thing, it's an asymptote, so it affects the behavior of a graph, right? We actually did have a horizontal asymptote here. If you could see it, it was right here. So that can be found by one of 3 scenarios, okay? So with horizontal asymptotes, what you want to look at is the degree of the numerator and the degree of the denominator. So you look at them as 2 different polynomials, the numerator and the denominator. You look at what's the degree of the numerator, and you look at what's the degree of the denominator. So the degree of the numerator, we'll call that n, and the degree of the denominator, we'll call that d. So these are the 3 different scenarios. If the n is greater than d, then there's actually no horizontal asymptote, okay? So if the numerator is greater than the denominator, there's no horizontal asymptote. So I just like to remember this with this statement right here. The highest degree is in the numerator, no horizontal asymptote. Now, if the degree of the numerator and the denominator is equal, then the horizontal asymptote will be the line y equals whatever the coefficient is of the numerator over whatever the coefficient is of the denominator. So in other words, in this example, right, you would have the horizontal asymptote would be 4 over 1. Since the degree of both is 2, right, then n equals d, and therefore the horizontal asymptote is y equals the coefficient of the numerator over the coefficient of the denominator. So the horizontal asymptote would be the line y equals 4. In this one, there was no horizontal asymptote, so that's why I didn't put anything there. There would be no horizontal asymptote here, okay? And you could see that the numerator degree is bigger than the denominator degree. Now, if it's the other way around, if the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is just y equals 0. There's nothing to calculate there. It's just y equals 0. So here, for example, the degree of the numerator is 1, and the degree of the denominator is 2. As long as the degree of the denominator is the one that is biggest, right, the highest degree is in the denominator, then the horizontal asymptote is just the line y equals 0. Okay? It doesn't matter. The numerator could be anything. The denominator could be anything. As long as the bigger degree is in the denominator, then the horizontal asymptote is y equals 0. So if it's biggest on top, no HOA. Biggest on bottom, y equals 0. All right? So let's do some examples. So identify the horizontal asymptote here. Okay, well, let's look at the degree of the numerator. It's 2. The degree of the denominator is 2. So the degrees are equal. N equals D. So the horizontal asymptote will be the line y equals the coefficient of the numerator, which is 3, divided by the coefficient of the denominator, which is 1. So the horizontal asymptote will be y equals 3 over 1, which is 3. So this is our horizontal asymptote. Let's do one more. I'm going to let you pause and try number 4 on your own. Okay, so looking at the degree of the numerator, we have 2, and the degree of the denominator is 5. So the bigger degree is in the denominator, which means that the horizontal asymptote is the line y equals 0. All right, and moving right along, now let's talk about oblique, or what's also called slant asymptote. So both of those are the same. Sometimes they call it oblique, sometimes they call it slant. It's like saying big and large. They're the same thing, okay? Now the graph of a rational function will have a slant if the degree of the numerator is bigger than the degree of the denominator, right? But by exactly 1, okay? So notice that that means that there is no horizontal asymptote, because this only happens, you only have an oblique if the degree of the numerator is bigger than the denominator by 1. Now specifically by 1, but it is bigger. So you cannot ever have both. You can't have both a horizontal asymptote and an oblique. You can only have one or the other, okay? Now you could have neither, but you can't have both. So you either have a horizontal asymptote or an oblique. You can't have both. All right. Now, how do we find that oblique, right? How do we find the line for that slant asymptote? Well, all you're going to do is you're going to divide the numerator and the denominator, and then disregard the remainder. Okay. So it'll just be y equals whatever the quotient is and disregarding the remainder. So for example, we have here x squared minus 2 divided by x minus 1. So you could see that the numerator is bigger than the denominator by exactly 1, the degree. So there is an oblique here. There's no horizontal asymptote. There's an oblique, and we find it by dividing. Now this is in the format x minus c, right? The coefficient is 1 and the power is 1, so we could use synthetic to find the oblique. So once you divide, you end up with 1 and 1. So remember, these are the coefficients. You always disregard the remainder. And we started with the highest power of 2, so we end up with 1x to the power of 1 plus 1. So this is the slant. That is the equation for the slant. Again, remember, all asymptotes are lines. So whether it's a vertical line, you have to write it as an equation, right? X equals whatever X value you cross at. If it's a horizontal line, whatever Y equals, whatever Y value you're crossing at. And a slant is just a line. It's a linear function, right? So you have to write the equation of that line. And the equation of that line is found by division. So let's do an example. Identify the oblique asymptote. Okay, so we're dividing here x cubed minus 3x squared plus 3x plus 1 over this quadratic. Now this is not as nice as before where it's in the format x minus c. So we're going to have to do long division. Okay. Remember, for long division, you want to fill in any holes if there are missing terms, but in this case we don't have any. We have 1x cubed minus 3x squared plus 3x to the power of 1 plus 1x to the power of 0. 1x to the power of 0, but I don't have to write the x to the power of 0. Okay. Then our divisor, which is going to go on the outside, is x squared minus 5x plus 6. Okay. Whenever I'm doing long division, I like to kind of work backwards because normally we're supposed to divide these two. But I like to think, what do I multiply x squared by to get 1x cubed? So I would have to multiply by x. So that's what I'm going to multiply by. I multiply by x. And now I multiply x to the entire divisor. X times x squared is 1x cubed. X times negative 5x is negative 5x squared. And x times 6 is 6x. Now I need to subtract. And remember to distribute the negative. So x cubed minus x cubed will cancel. Negative 3x squared minus negative 5x squared would be negative 3 plus 5 is 2x squared. And 3 minus 6 would be negative 3x. Now we can go ahead and bring down the positive 1. And we go ahead and we ask ourselves the same question. X squared times what would give me 2x squared? So it would be x squared times 2. So I'm going to multiply everything by positive 2. 2 times 2x squared. Actually, I don't even need to do this part. I just need to find what it is, because whatever I get here for multiplying 2 times this, I would then subtract these two, and then I don't have anything else to bring down. So this would be my remainder. But I disregard my remainder anyway. So it's no use in me doing all the math because that information is not going to be useful for me anyway. All I care about is the oblique, and I disregard the remainder anyway. So here is my quotient. So the oblique line, the oblique asymptote would be y equals x plus 2. All right. Go ahead and pause this video now and try number 6 on your own. All right, so let's take a look at number 6, right? Now, this one, luckily for us, we have a coefficient of 1 and a power of 1, so we could use synthetic for this one, all right? Now, using synthetic division, remember that C is the opposite of what you see, so what goes on the outside is what would be the 0, right, which is 2. And then the coefficients of all of my numerator terms. Now, normally, if I had a missing term, don't forget, you always have to add a 0 for a placeholder, but in this case, I don't have that going on, so those are my coefficients. Bring down the first term, and then you multiply. 2 times negative 3 is negative 6. Add 1 plus negative 6 is negative 5. Then you multiply again. 2 times negative 5 is negative 10. And actually, you don't even need to do this last part because we disregard the remainder anyway. So there we go. The highest power that I started with in my numerator is 2, so I'm going to start with x to the power of 1. So negative 3, x to the power of 1, minus 5. So that is the equation of the oblique. Y equals negative 3x minus 5. All right. Awesome. So let's bring it all together and find all of the different asymptotes of some rational function. So we're identifying points of discontinuity, any vertical asymptotes, holes. We're also identifying any horizontal asymptotes or slant asymptotes. And remember, slant and oblique is the same. So what I'm going to do is I'm going to factor. Okay, I'm going to factor the denominator and I'm going to factor the numerator because I want to see if anything cancels, right? I'm going to need the vertical asymptote. I'm going to need any whole. I'm going to need, is there a horizontal asymptote? Is there an oblique? And those are the things that I'm looking for. So let's start with factoring. So we can factor out 4 from the numerator. We get x minus 2. In the denominator, this would factor into x minus 3 times x minus 2. So we do have an x minus 2 that cancels. So because that cancels, that is our x value for our whole. So x minus 2 cannot equal 0, which means that our whole x value is 2. And then this factor did not cancel, so that is where we get our vertical asymptote from. And that 0 would be with an x value of 3. So the vertical asymptote is the line x equals 3. And I need to now find the y value for my whole. Okay, so I need to find what is the y value when x is 2. Remember, you want to use the simplified version of your function. So f of 2, I want to find that output. The numerator is 4, the denominator is x minus 3, so 2 minus 3. 2 minus 3 is negative 1, so we end up with 4 divided by negative 1, which is negative 4. So that is the output for the input 2, and that is our whole. Next up, let's look at our horizontal asymptote. Now, looking at the numerator, right, the degree is 1. And looking at the denominator, the degree is 2. So the degree is bigger on the bottom. The degree is bigger on the bottom. Our horizontal asymptote is y equals 0. Okay? Again, look at horizontal asymptote is the degree is bigger on the bottom, the denominator, then your horizontal asymptote is y equals 0. Now, that means that we actually do have a horizontal asymptote. So that means that there is no oblique. All right, let's move on to number 8, and then I have a couple for you to try on your own. So same question, okay, we need to find the vertical asymptote, we need to find any whole, we need to find any horizontal asymptote, we need to find any oblique or slant. All right, so again, we're gonna go ahead and factor. Numerator would factor into x plus 3 times x minus 1. The denominator, we could factor out 3 from both, and that would give me x plus 2. So nothing cancels here, which is fine, okay? So we don't have a whole because the wholes only come from canceling a factor on numerator and denominator. But we do have a vertical asymptote, right? This is a factor that stayed alive, so x is negative 2 would make this 0, so our vertical asymptote would be x equals negative 2. And that is an equation, right? Horizontal asymptote, let's take a look. The degree of the numerator is 2, the degree of the denominator is 1. So the degree is bigger in the numerator, which means that there is no horizontal asymptote. Now, the degree is bigger by 1. So there is an oblique. We now need to find this oblique. We're going to do that by dividing, and the coefficient is not 1, so I'm just going to use long division. So I have x squared minus, plus 2x minus 3, and I'm dividing that by 3x plus 6. Now, what times 3x would give me x squared? 1/3 x. 1/3 times 3 would give me the coefficient of 1, and then x times x would give me x squared. So 1/3 times 3x would give me 1x squared. 1/3 x times 6 would give me positive 2x. Then I'm going to go ahead and subtract these two. Anything minus itself is 0, so we just get 0. And then we're going to bring down the negative 3. Okay, so we get 0x, this cancels. Now, there is nothing that I can multiply by 0x to get 3x, right? It's just multiply by 0. So this is just 0. And 0 times anything would be 0, and we would get a remainder of negative 3. But the remainder is disregarded anyway, so it doesn't matter. So our equation is just 1/3 x. Y equals 1/3 x, and that is the line for the oblique. All right, so go ahead and pause this video now and try 9 and 10 on your own. Okay, so Looking at number 9, right, we're 9 and 10, we're asking the same question. So we still want to find what's the vertical asymptote, what's the hole, what's the horizontal asymptote, and what's the slant or oblique. Now, we're going to do that by factoring. Let's go ahead and factor the numerator first. That would factor into x plus 3 times x minus 2. The denominator, we can factor out first 4 from all terms, which gives us x squared plus 5x plus 6. And then now we can factor that into x plus 1 times x, x plus 2 times x plus 3. Ooh, I'm deleting too much. X plus 2 times x plus 3. All right, so let's see, does anything cancel? Yep, the factor x plus 3. So that means that I do have a hole at the x value that would make this a 0, which is -3. Now we do have to find that y value. Remember, you want to use the simplified version. F of -3 equals -3 minus 2 over 4 times -3 plus 2. -3 minus 2 is -5. -3 times plus 2 is -1. -1 times 4 would be -4. Negative divided by a negative is a positive, so we get 5/4. All right, now vertical asymptote. We do have this factor that remains. So we have a vertical asymptote at x equals -2. And horizontal asymptote, well, the coefficient, the degree of the numerator and the degree of the denominator is the same. So we're going to do the ratio of the coefficients. The coefficient in the numerator is 1, the coefficient in the denominator is 4. So the horizontal asymptote will be the line y equals 1/4. And because there is a horizontal asymptote, that automatically means that there is no slant. All right, let's try number 10. Okay, again, same thing, we want to factor, right? So first, let's go ahead and factor out a common GCF of x in the numerator. So we got x squared minus x minus 12. And in the denominator, we can factor out a -4 GCF. That gives us x squared plus x minus 2. Now we can continue factoring that further. Multiplies to -12, adds to -1 will be -4 and 3. So this will factor into x minus 4 times x plus 3. In the denominator, multiplies to -2, adds to 1 would be 2 and -1. So this will factor into -4 times x minus 1 times x plus 2. All right, now let's take a look. Does anything cancel? No. So let's write out our little blanks here so we can fill them in. Hole, horizontal asymptote, and then slant. Okay, so there are no holes because there is no factor that cancel it out on top and bottom. We actually have 2 vertical asymptotes in this case because we have 2 factors in the denominator that stayed. This would give me x equals 1. And we have another vertical asymptote at x equals -2. So we have 2 vertical asymptotes for this function. Now, horizontal asymptote, let's take a look at the powers. The numerator power is 3, the denominator power is 2, so the higher power is in the numerator, which means that there is no horizontal asymptote. Now it's bigger by 1, so there's a slant. Let's find the slant. So I'm going to divide. I'm dividing x cubed minus x squared minus 12x, and then I need to put a 0 for a placeholder for the constant. And I'm dividing that by -4x squared minus 4x plus 8. Okay. What do I multiply -4x squared by to get x cubed? Well, negative, because I need it to become positive. 1/4, because I need it to multiply to +1. And I need to multiply by x so that I could get the x squared to be x cubed. So -1/4 times x times -4x squared will give me that 1x cubed. -1/4 x times -4x would be +1x squared. And -1/4 x times +8 would be -2x. Now we can go ahead and subtract these two together. negative 1 minus 1 would be negative 2x squared. Negative 12 plus 2 would be negative 10x. And then we're going to bring down the plus 0. Now, what do I multiply negative 4x squared by to get negative 2? Well, I have to multiply by 1/2 to get it to be negative 2. And then x squared is already x squared, so that's it. 1/2 times negative 4 x squared would be that negative 2x squared. 1/2 times negative 4x would be negative 2x. 1/2 times 8 would be positive 4. And then we would subtract. Actually, this would give me the remainder, which I disregard anyway, so I don't need it. My slant is the line y equals what's up here? Negative 1/4 x plus 1/2. All right. Okay, so that is asymptotes. The last thing that I want to cover in this video, just because it's really quick and easy, is x and y intercepts. That's another key feature of rational functions that we're going to need. Now, we've done this a trillion times before, right? To find the y-intercept, you substitute 0 in for x and solve for y. To find the x-intercept, you substitute 0 in for y and solve for x. Now, the important thing here is to always use the reduce function, okay? Just like before, when we're finding the y value of the whole, you want to make sure that you're using the simplified version of the function, the reduced version. Same thing for x and y intercepts. So you want to reduce it first, if possible. So let's go ahead and find the intercepts here. This would factor into x plus 2 times x plus 3. And the denominator is x minus 4. So nothing canceled here. So this is our reduced function as much as we can. So I'm going to go ahead now and find the y-intercept first by plugging in 0 for x. So f of 0 would be 0 plus 2 times 0 plus 3 over 0 minus 4. Now 0 plus 2 is 2. And 0 plus 3 is 3, so we have 2 times 3 in the numerator, and 0 minus 4 is negative 4. So we end up with 6 over negative 4, and reducing that by dividing 2 on top and bottom, we get negative 3 over 2. So that is the, we set x to be 0, that is the y-intercept. So the y-intercept is negative 3 over 2. Now let's find the x-intercept, okay? Now to find the x-intercept, I'm going to set the y value to be 0 and solve for x. Okay, now to solve for x, first I need to get rid of this denominator. So I'm going to multiply by x minus 4 on both sides. That will cancel out the x minus 4, and the left-hand side would give me 0. So in other words, we're just finding what makes the numerator 0. This would give me x equals negative 2, and this would give me x equals negative 3. So these two are my x-intercepts. Okay, so go ahead and pause this video now and try number 12 on your own. All right, so last one, here we go. Factor the numerator, right? We want to factor out a GCF of 2 first, so we could factor that out. That would give us x squared plus 5x plus 4. And then the denominator, of course, is still the same. And then I could factor this further. The numerator would factor into x plus 4 times x plus 1, and the denominator is x minus 4. Okay, so actually nothing canceled here either, but remember, if something does cancel, make sure that you are using the reduce function to find the intercepts. Okay, so first let's find the y-intercept, so set x to be 0. So we have 2 times 0 plus 4 times 0 plus 1 over 0 minus 4. So we have 2 times 4 times 1 over negative 4. 2 times 4 times 1 would be 8. 8 divided by negative 4 is negative 2. So this is our y-intercept. And oh, by the way, side note, you can have at most one y-intercept, but you can have multiple x-intercepts, okay? Kind of like with vertical asymptote, where you can have more than one, but you can only have one horizontal asymptote or oblique, right? So you can have more than one x-intercept, you can only have up to one y-intercept. All right, next let's find the x-intercept. So I'm going to set the y value to be 0. And I'm going to solve for x. So I'm going to multiply by the denominator to get rid of it first. That's terrible, x minus 4. Okay, there we go. So that'll cancel the denominator and give me 0 on the left. So 2 times x plus 4 times x plus 1. So we have 2 zeros, one at x equals -4 and another one at x equals -1. You won't always have 2 x-intercepts. It just so happened that in this case, there were 2 examples that had 2 x-intercepts. So I hope that that was helpful, and I'll see you guys in the next video. Bye!